In this lesson, we're reviewing modeling using exponential equations, and as we have a better understanding of logarithms now, it should be easier to apply and solve in these scenarios. For review, the general form of an exponential function is y is equal to a times b to the power of kx, where a represents the original value when x is equal to 0, b will be the rate of growth or decay. So, for example, if we're doubling, then b will be equal to 2. If we're increasing by 50%, then b will be 1.5. If we're decreasing by 20%, then b will be 0.8, and so on. And k is a growth decay constant. It allows us to adjust for timing and so on. So in this lesson, we're going to focus on modeling from simple scenarios. We'll look at modeling half-life scenarios, and then finally we'll look at modeling from data, both algebraically and with a graphics calculator. We'll jump straight into it as this is a review. So this first example says a bacterial colony is doubling every 15 minutes with an initial count of 1,000. Create an exponential model of the population growth and determine the population size after 10 hours. So in this scenario, we can see straight away that we're looking at the form y equals a times b to the power of kx, because it tells us it's an exponential model. We know that a will be 1,000, b will be 2 because it's doubling, and we need to calculate k. Now at the same time, we're going to replace y with n for number in the population, x will be replaced with t, and we need to find k. And to find k, we will use this information as doubling every 15 minutes. So when t is equal to 15, n will be equal to double the initial, which will be 2,000. So here's our base model. N is equal to 1,000 multiplied by 2 to the power of kt. If we put in our first bit of information, t is 15, n is 2,000, we can find k. So 2,000 is equal to 1,000 multiplied by 2 to the power of 15k. So if we divide both sides by 1,000, we've got 2 is equal to 2 to the power of 15k. And we don't have to use logarithms in this case. We can use index equations. We know that 1 is equivalent to 15k. So therefore k is equal to 1 on 15, and we've got our model. N is equal to 1,000 multiplied by 2 to the power of 1 on 15t. Now all we need to do is put in our time. T is equal to 10 hours, which means we're looking at 600 minutes. So n will be equal to 1,000 multiplied by 2 to the power of 1 on 15 times 600. So if we type this into our calculator, 1,000 multiplied by 2 to the power of 1 over 15, and then multiplied by 600, we get 1.1 times 10 to the power of 15, which is quite a large number in that bacterial colony after 10 hours. Okay, so hopefully that makes sense. We're going to get into the habit of calculating k, because that's a process that we're going to use over the entire course, year 11 and 12. Okay, so when we look at our second example, we've got a half-life scenario. In a half-life scenario, we're looking at the b value being 1/2 or 0.5. In this case, we're just given a statement of the original mass. So we're going to let A equal m0, which stands for the original mass. Instead of y, we're going to use mass, and instead of x, we're going to use time. Now, in order to find k, we're going to look at after 1,000 years, so when t is equal to 1,000, m is equal to 64.7% of the original, which means it's 0.647 m0. Okay, so we've got everything we need. Now y is equal to a times b to the kx where A is m0, B is 1/2, K is unknown, and we have time, which is 1,000 years. Y will be equal to 0.647 MO. Now, if we divide both sides by MO, we can see this cancels, and we've got 0.647 is equal to 1/2 to the power of 1,000 K. Here we want to use our logarithm, so if we put this into logarithm form, we have log base 1/2 of 0.647 is equal to 1,000 K, and therefore K will be equal to log base 0.5 of 0.647 over 1,000. So when we put this into our calculator, K should end up being 0.0006282 approximately. And now we've got that, we can write our rule, which is m is equal to m0 multiplied by 1/2 to the power of kt, which is 0.0006282t. Now what we're looking for to be able to calculate the half-life is that we want to know what the time is equal to when the mass is 1/2 of the original mass. So when it's half of the original, there's a half-life. So we have 1/2 m0 is equal to m0 multiplied by 1/2 to the power of 0.0006282t. We can divide both sides by m0. So now we've got 1/2 is equal to 1/2 to the power of 0.0006282t. Now here we should be able to see, using index equations, that 1 is equal to 0.0006282t, and therefore t is 1 on that. And so t will approximately be 1 divided by the answer, which is 1,591.95 years. Okay, so essentially it's the same idea. We use our logarithms or our process to calculate k. So calculate k, and then once we've got that, we can use whatever solving process we need to isolate the unknown in the scenario. In this case, it was the time when the mass was equal to 1/2 of the original. Example 3, we're looking at a totally different scenario. We're given our base function y is equal to a times b to the power of x, so we're ignoring k this time. It's saying a must be greater than 0 and b must be greater than 0, and we're trying to find the values of a and b. Now we're given 2 points, so we know that when x is equal to 1, y is equal to 6. And if we put that into our equation, we've got 6 is equal to a times b to the power of 1. Or simply just 6 is equal to a times b as our first equation. When x is equal to 5, y is equal to 96. And when we put that in, we get 96 is equal to a times b to the power of 5. And there's our second equation. Now, with solving exponentials, the easiest way to solve simultaneously is with division. So if we look at equation 2 divided by equation 1, we end up with 96 is equal to a times b to the power of 5 divided by 6 and a times b to the power of 1. So 96 on 6 is 16. The a's will cancel, and we have b to the power of 5 over b to the power of 1, which is b to the power of 4. And to isolate b, we're looking at the quartic root, and we don't have to worry about the negative side of this because a and b must be positive. The quartic root of 16. So we end up with b is equal to 2. Once we've got b, we can sub b equals 2 into either one of the two equations. I'm going to choose the first equation. So 6 is equal to a times b, which is 2. A is therefore equal to 3. And so therefore we end up with the equation y is equal to 3 times 2 to the power of x. So there's our solution. B is 2, A is 3, and here's a model that fits the scenario. Okay, so example 4, we're looking at using the graphics calculator to sketch and to model an equation. So the question says the table shows the increase in weight of Samu, an orangutan, born at the Eastern Plains Zoo. And part A, we want to draw a graph to show Samu's weight increase for the first 6 months. And part B, we want to model as an exponential equation to represent Samu's weight. So part A, what we're going to do is we're going to use our graphics calculator. So we're going to hit menu. So menu. And we're going to go into statistics. So menu, stats. In list 1 and list 2, we're going to enter the data. So the first column will just be the 0, 1, 2, 3, all the way to 6. There we go. And the second column will be the values in kilograms, 1.65, 1.7, 2.2, 3.0, 3.7, 4.2, and 4.8. So once we have all that, we're going to hit graph. Now we should check our setup. So if we hit setup here, we're looking at a scatter with list 1 versus list 2, which is what we want. If you have something different, you need to fix that. So for example, if it's not a scatter, you need to go into graph type and choose scatter. If it's not list 1, you can choose list, and we can make it whichever list we want. I still want it to be list 1. Okay, so we'll hit exit, and now we hit graph 1, and there is my rough sketch. So if I've got months versus weight, then I've got a graph that looks similar to that. Now part B, we're looking to model. So in order to model on our graphics calculator, we want to use that calc function. So we want to hit F1 and calc. Once we hit that, we have to choose the type of function that we want to apply. Now, exponential isn't on this one, so we're going to go across, and you can see that when we hit F6 and we go across, then we can choose F3 for exponential. Now there's two forms here. We haven't started talking about AE to the power of BX form, so we're going to look at F2, which is AB to the power of X. From there, we get our A value and our B value, and we're looking at the form y equals A times B to the power of X. So A is 1.553 and B is 1.218. So I can say that my model is y is equal to 1.553 multiplied by 1.218 to the power of x, where y is actually our w and x is actually m. So we can say this is my weight is equal to 1.553 by 1.218 to the power of m, which is time in months. And there we have it. That's how we get an exponential model from a graphics calculator and data. Just to show you, we could do the same thing with the last problem. So if we go all the way back and we get rid of all this information, delete and delete, and we put in our 1 and 5 for the x values, and we put in 6 and 96 for the y values, and we graph. We've got our 2 points there, and we go into calculate and exponential. we can see we get the same thing. A is 3, B is 2, and so on. Okay, so that's the skills that we need to have for modeling exponential equations. You'll need to practice, go through the examples, and get to a point where this is fairly fluent. You can use your logarithm skills within exponentials without too many issues. Okay, thank you for listening.